intermolecular forces and intramolecular forces. We'll first look at intramolecular forces, and just by the prefix over here, you can kind of tell that it's within, because intra stands for within, whereas inter, like international, is between, let's say, different countries. Intra is within that country, so it's within the actual molecule. So let's first state here it's a force that bonds atoms to one another, but specifically within the molecule. Within the molecule. I'm just going to put here in brackets that it's very strong, because this is how life is able to be stabilized and remain intact, because of these intramolecular forces that keep it from separating. Now let's have a look at the intermolecular forces. And like the prefix says, inter, it kind of out branches. So let's have here written it's a force that attracts, or bonds as well, so it attracts or bonds molecules to another. Maybe I'll write here two other molecules. And put here it's weaker. Then the strong intramolecular forces. Let's have a look at different types of these intra and intermolecular forces. We'll start down here with metallic, the metallic bonding, and then continue to go up this ladder, and the higher up you go, the stronger the intramolecular force is. For metallic, it's when positive ions, so in our case right here, it's the metals, because obviously they're positive ions. So positive ions, they're floating in the electron C. If you're confused about the electron C, please look at the previous video that I made regarding melting point. It's pretty much an area where the electrons are free floating around the particular ions, going from one to another. And it's kind of being shared, being passed around. So just surrounding it. So that's metallic. Next we have covalent. And then we have ionic. Now, for the metallic bonding, a particular example, let's say, is maybe aluminum. And this electrons that it lost, because it's a 3+, so it lost the 3 electrons, they'll just be floating in the electron C and participating in certain electrostatic attractions and other interactions in the electron C, and those electrons can be passed around to other ions there as well. Hence why it is quite malleable when we look at metallic bonds. Next we have covalent. Covalent is when the electrons are shared. Now this is important here. They could be shared evenly or not evenly. All right, electrons are shared evenly or not evenly with bonds that have a specific direction. Now, an example of covalent bond could be, let's say, H2, our hydrogen gas, for example, because we have our our non-metal here and another non-metal here, and they're bonded together in such regard where this valence electron from the hydrogen and this valence electron from the hydrogen are bonding. It's not that this electron belongs maybe 95%, 99% with this hydrogen. They're both shared quite evenly. Next we have ionic. Now for an ionic, it's when the ions are strongly attracted. So when the cations and the anions, so when they're strongly attracted. Okay? And not sharing electrons. In contrast to this one, this is all about sharing the electron, so it's not as strong. Ionic, not sharing the electrons, so it all pretty much belongs, the electrons that are being passed from one ion to the other. It belongs a lot more to one over the other. And this tends to be a lot more powerful. So an example of ionic, classic example of NaCl. Now let's have a look at some intermolecular forces. We'll start from the bottom down here with London dispersion. And like the previous example, we'll increase on our way up. So let's start with London dispersion. London dispersion, it's when there's a temporary dipole. Temporary dipole is induced by proximity of another molecule or atom and the nucleus is attracted to its own and others' electrons. Let's look at an example. Fluorine here, again it's a diatomic, so there's two of them. And it's interacting, I'm doing it in dots, a dotted line here, it's interacting with another fluorine diatomic. What is going on? Well, these electrons are interacting with each other from this one over to here and this one over to here. And there is an induction by the proximity of another molecule. So this is in proximity with this, and this is in proximity with this. The electrons here want to pull these guys in that direction, but this one also wants to pull these guys in that direction. So there is a temporary dipole that is induced because these also within these intramolecular forces have positive and negative charges going from one end to the other. However, this and this are the same element, so it's kind of like a tug of war between the two. There's not one end that is slightly positive and one end that is slightly negative, because then we have a dipole. In this case, there is no dipole. Same thing here, no dipole. So when there is some sort of attraction between these two, it's solely the weakest force possible, because there's no dipole at all. So non-polar molecules tend to display London dispersion only. The electrons, for let's say here, and the electrons for say here, are going to be attracted to its own nucleus, so this own nucleus. But these electrons are also attracted to maybe the nucleus in there. And the electrons out here are attracted to its own nucleus, but also attracted to the nucleus over here as well. So this interaction is called London dispersion. Now, the smaller molecules tend to be gaseous because they don't have as many elements in question, and that would mean the effective nuclear charge is not as large, so there's going to be less amount of electrons, less amount of protons to accompany it. However, larger ones can be of a liquid state because of higher effective nuclear charge, because more protons and more electrons. Now let's have a look at dipole-induced. When looking at dipole-induced, you have a dipole charge, so a polar molecule. Okay, a dipole charge, and it can polarize, any neighboring molecules. So an example of this one would be, let's say, oxygen gas, and we have H2O over here. This side is going to be slightly negative, and this side is going to be slightly positive. This side is going to be slightly positive as well. Here, of course, they are of the same magnitude, so there's going to be a tug of war going on in here. One side is not slightly positive or not slightly negative than the other. And then let's have a force of attraction between these two, for example. And of course, between these, due to a higher electronegativity of the oxygen, it's going to go in that direction. And then same thing here. It's going to go in that direction. A good example of this is fish breathing. This is a great example because water has oxygen. So the oxygen that's within the water, that's an intramolecular force, but we're looking at the intermolecular force. And if we're looking at intermolecular force, we're more concerned about this bond over here. Because guess what? Oxygen doesn't just exist within the H2O molecule, it's also intermolecularly bonded as well. So for the fish to get oxygen into their gills, it's going to be quite easy to take it apart from this water, because it's not a very strong intermolecular force. It's still down here at the ladder. So it's going to be quite easy to rip off this oxygen and go into the lungs, and then the fish can breathe. So this is a dipole-induced. Next we have a ion-induced. In an ion-induced, we have an ion charge, and it can polarize. Let's have a look at same thing, our oxygen, and let's have it with this ion here of iron. What is a good example for this one? Well, it's hemoglobin and the diffusion of oxygen. In the cells. Okay. In case we wanted to put the dots here, we could have done that as well. All right. When we have iron is a very important element that makes up hemoglobin. Hemoglobin is a protein in your body. It helps carry around oxygen and even carbon dioxide as well, but it's mostly known for the oxygen. It carries it around, and it's about 70 times more efficient to carry this oxygen with hemoglobin as opposed to not. This iron, major constituent of hemoglobin, like I said, is going to be carrying this oxygen. And of course, it would not be suitable for this oxygen to fall off. So it needs to be a stronger hold on this hemoglobin that's made out of this iron, so that it can get to different areas in your body and diffuse into the cells whenever it jumps off. And then it's going to diffuse. So it must be stronger than, let's say, a dipole-induced, because it would be very, very non-beneficial and not practical for this to fall off easily. So it's going to be a stronger hold, but it obviously cannot be too strong. That's why it's not up here. It's kind of in the middle, but still on the lower side of the ladder. Next, let's look at dipole-dipole. Looking at the dipole-dipole, it's when the oppositely charged dipoles of different molecules are attracted. Let's have a look at an example of this one. If we have, let's say, HCl and HCl, of course we're going to have some dipole in that direction. It must deal with polar molecules only. Dipole-dipole must have polar molecules only. This is quite powerful because both molecules have a side that is more negatively charged, as shown here, right? More negatively charged, and the other side being more positively charged. This side more negatively charged, this side more positively charged. So there is a longing for attraction. It's kind of desperate to want to be there. This negatively charged desperately wants to go to this positively charged end. And if we even change, let's say, the orientation here to make it easier to comprehend, if it's in a tetrad format like this, you notice how it's very, very well held together. Positive, negative, positive, negative. And in other molecules, when bonded with other molecules that it's neighboring, if it's in this kind of structure, it could be very, very strong. So covalent network bonding could be an example of this one as well. Now let's have a look at hydrogen bonding. Hydrogen bonding, it's when you have a proton. So in this case, it would be the hydrogen. Hydrogen will be the proton. It's shared between two electrons and the central atom. That is lone paired. I'll put it in here as LP. That is lone paired and high En, also known as electronegativity. Now, in order for hydrogen bonding to display these characteristics, best thing to do is, first let's look at an example. Let's have a look at H2O. And let's have another H2O over here. And another H2O here. If we look at our H-NOF principle, H is going to be our proton, and it's shared between two electrons, but which one is going to be the central atom? Is it going to be N? Is it going to be O? Is it going to be F? All three of these could work. Hydrogen bonding tends to be H-NOF. H with an N, H with an O, or H with an F. This is because they have a low atomic radii. A low atomic radii with a large one, like hydrogen, is when the electrons are closer together towards a neighboring nucleus, so it has a high electronegativity. You can just do the electronegativity calculation. You can look for the electronegativity of H and look at the electronegativity of N, do the difference. It's going to be quite high. Same thing with H and O, find the difference, quite high. H and F, same deal. They tend to be on the top right corner of the periodic table. And of course, it must be the central atom. If we look at this end, which is slightly negative, this end slightly positive, slightly positive, slightly positive, slightly positive, slightly negative. Let's have this attraction here with this dotted line together. This here is a hydrogen bond because it's going with from an H to a neighboring O. That is a hydrogen bond, as witnessed here. It's going to be a lot of cohesion because of this electronegativity difference. This is why H2O is a very, very powerful solvent. It can dissolve many, many, many things. It can also be used for surface tension as well, which is more of an adhesive property. So if I were to show you, let's say, a little beaker here, or maybe let's say a graduated cylinder. Let's say we have a liquid here. Sometimes you may notice something like this, where it's a little bit of a convex shape. So right over here, it kind of looks convex as opposed to concave, right? Concave would be like that. This is the opposite. It's a convex shape. What is going on? It's because this liquid has very strong cohesive properties. Cohesion, being together with one another. So whatever liquid this is has very, very strong cohesive properties, binding together very, very well, more than its adhesive property. Adhesive means it would stick on the side of this cylinder. So which one's going to be stronger? The adhesive portion where it sticks on the side, or the cohesive portion where it's, again, thanks to the due to gravity as well, but also its cohesive properties between the molecules. Which one is going to be stronger? The cohesive aspect here, or this adhesive aspect where it sticks on the side of the cylinder? It would be cohesive. So in this case, the cohesiveness is greater than the adhesive property. Hence why it's not stuck on the sides and is more so giving this this convex kind of shape, bulging outwards. Now, hydrogen bonding also exists within the DNA as well. So when you have a phosphate group, a sugar, and then nitrogenous bases, the two different nucleotides that are going to be stacked right beside each other, the nitrogenous bases of one end with the nitrogenous bases of the other end are connected by hydrogen bonds, because that determines sequencing. If that breaks, that's very dangerous. So again, hydrogen bonding is very strong, that cohesive property, not only just shown here with the electronegativity differences, but also shown here as well, and also with the DNA. Hydrogen bonding has to be very, very powerful. It helps keep and sustain life tightly packed together so it doesn't break apart. Now let's look at the ion-dipole. An ion-dipole, it's when the ion charge is with a dipole charge. Why is this important? Well, if we look at the classic example of NaCl, let's say it breaks apart. Let's say like Cl minus here, and then let's say Na plus here. If we have a H2O molecule, it breaks apart that Na quite easily, because the Na crystalline structure does not want to be with one another as badly enough than being taken away from the water molecule. The water molecule is greatly favored when it pulls it apart. And you could do the same thing here with this H2O with that Cl. And it's just pulling it apart, so it's very powerful. An example of this, again, like I said, with the NaCl structure, because I believe NaCl to be in a molten state, so for it to actually split apart requires a high amount of temperature, I believe 800 degrees Celsius. Yet water can do that like it's nothing. So ion-dipole is definitely very, very top of this ladder. Let's look at some questions that we'll do together. So if we have lithium nitrate and it dissolves in water, again, dissolves, so let's have it break apart. So let's have Li over here and NO3 1 minus over here. If we have water, obviously this side's more negatively charged, this one's more positively charged, this one's more positively charged. You have an interaction where it breaks it apart like that. Same thing with this one over here. This one's going to be the pluses. Again, slightly negative over here. And you're going to have an interaction of it being pulled apart. What are we looking at? Well, we over here have ions. What do we have over here? What we have is polar molecule. Same thing here. We have a polar molecule. This here is an ion. So polars exhibit a dipole charge. If you look at that sheet a few seconds ago, for the polars, has a dipole charge. Ion would be an ion dipole. If we look at number 2, so this was number 1. If we look at number 2, we have chlorine gas that can dissolve slightly in water. And they are exhibiting a pull, a tug of war between one another, but one side is not more positively charged or one side is not more negatively charged. There is an equal distribution. Then we have its ability to dissolve slightly in water. Let's have water over here. And you have this interaction. And we're able to have this interaction because it says that it dissolves. If it doesn't dissolve, then we shouldn't be able to kind of see this here. Because there is this interaction, we have to now state what are we looking at from both regards. This one here is a nonpolar. So it's likely being induced. This one over here is a polar. So it's doing the inducing. So what do we have? Therefore, we have a induced dipole or dipole-induced. Dipole is for the polar, and then the nonpolar that is being induced by this polarity, right? This is polarizing these. It is being induced, so it's dipole-induced. Now let's have a look at number 3. Carbon dioxide dissolves better in water than oxygen. So let's have a look at carbon dioxide. C. This is going to be a nonpolar molecule. We can just state it right away. It's quite obvious it's nonpolar. Carbon dioxide dissolves better in water than oxygen. So let's draw water over here. And then we have oxygen over here. Let's look at some interactions. Carbon dioxide dissolves better in water than it does with oxygen. Why is this the case? Because there are more separation of charges. Positive, slightly negative due to electronegativity difference. This one over here, slightly positive, slightly negative. It's because there is a lot of separation of charges here. It's going to want to go and be polarized with another molecule that is polarizing. This here is slightly positive on this end, so it's likely going to want to interact this way. It definitely would not want to interact this way. It would not want to do that because this is not polarizing. It's a lot more favorable to go be polarized with this one because these at least have ends that are clear-cut as slightly positive or slightly negative. This non-polar one doesn't do that. So therefore, CO2 will be dissolved better with water due to its separation of charges. Now let's look at our green questions of the day. Please give this a try on your own. Please pause the video and try to eloquently describe these statements. Number 1, water is cohesive. Number 2, wax will not dissolve in water. And number 3, iron dissolves in both water and hexane. If you want to know what hexane is, it's C6H14. Please give this a try on your own with as much detail as possible, and I will give you the answer shortly. This is the answer for number 1. This is the answer for number 2. This is the answer for number 3.